Hello there, and welcome to the Sleepy Nature Channel. Tonight, we are going to travel somewhere very far away, and also very, very close. Did you know that the little atoms inside your body, the tiny invisible pieces that make up your hands, your breath, your heartbeat, they were born inside stars, real stars burning bright in the sky, billions and billions of years ago, long before Earth existed, long before oceans or trees or birds. Those stars were quietly making the very stuff that would one day become you: carbon, oxygen, iron, all of it forged in the heart of a glowing sun, and then scattered gently across space, drifting for ages and ages until somehow, softly, it all came together into you. Take a slow breath now. Let your shoulders drop. Let your hands rest where they are. Tonight, we'll follow the quiet journey of starlight, from the very beginning of the universe, all the way to this moment, this soft, warm moment, where you are lying here, breathing gently, made of the most ancient and beautiful material in all of existence. There is nowhere else to be. Just here, just this slow, star-filled night. Imagine the very beginning, not a loud beginning, but a quiet one, like the moment before you open your eyes in the morning when the world is still wrapped in softness and everything is possible. That is how some scientists think about the very first moments of the universe. Not a violent crash, but a kind of unfolding, a gentle expansion, like a breath slowly being released into the dark. In those first moments, there was mostly hydrogen. Just hydrogen, the simplest, lightest element, the first thing the universe ever made. Tiny, invisible, drifting. And yet, already, even then, something extraordinary was beginning. Gravity, that soft and patient force, was drawing those little atoms toward each other, slowly, gently, the way sleep draws you down into warmth when the room is quiet and still. Clouds of hydrogen drifted through the young universe for hundreds of millions of years. There was no light yet, not the kind we can see. The universe was dark and cool and very, very patient. Scientists call this time the cosmic dark ages, and there is something peaceful about that name. A great rest, a long pause, before the first stars began to wake. Then, in some of those vast, slowly spinning clouds, something shifted. Gravity gathered enough hydrogen in one place that the pressure at the center became enormous, and the hydrogen ignited. The very first star blazed into existence. No one saw it. There were no eyes yet. But across the darkness, a warm light appeared, and the universe was no longer entirely dark. That first star was probably enormous, many times larger than our own sun. It burned hot and bright and fast, the way some fires do when they are given too much fuel. Inside its core, something remarkable was happening. Hydrogen was fusing together into helium, releasing energy as light and heat. The star was an engine, quietly and steadily building new elements from the simplest ingredients. As a massive star ages, its core keeps building heavier and heavier elements. Helium fuses into carbon, carbon into oxygen, oxygen into silicon, silicon into iron. Each step is a kind of quiet alchemy, a transformation so deep inside the star that we can barely imagine it. And yet, every atom of carbon in your body passed through exactly this kind of process, somewhere, someone, long ago. Iron is special. When a massive star's core fills with iron, it can no longer release energy from fusion. Iron absorbs energy rather than releasing it. And so, in a moment that happens in less than a second, the core collapses. And then, In a kind of final, generous exhale, the star explodes. A supernova, the most energetic event in the universe outside of the Big Bang itself. But even in that explosion, there is a gentleness to imagine. Because what the star is doing in its last moments is giving. It is scattering everything it ever made, every atom of carbon and oxygen and iron and gold, out into the surrounding space like seeds thrown by a very old, very tired hand into the dark soil of the universe. Those atoms drifted. They mixed with other gases, other clouds, other leftovers from other stars. They tumbled slowly through space for millions of years, the way a leaf tumbles slowly down a still autumn stream, unhurried, going wherever the current carries it. There was no rush. The universe is very good at being patient. Some of those atoms eventually drifted into a new cloud, a quiet, spinning cloud of gas and dust in one unremarkable corner of one galaxy. This cloud, too, began to collapse under its own gravity. At the center, a new star began to form, our sun, and around it, the leftover material began to clump together, first into dust grains, then pebbles, then rocks, then small worlds, and eventually, slowly, into the Earth that formed from that collapsing cloud, carried within it all the elements scattered by those ancient stars: carbon, oxygen, iron, silicon, gold, nitrogen, sulfur, every element that makes up the rocks and the ocean and the air, all of it recycled, all of it inherited from stars that burned and died before our sun was even born. Early Earth was not the soft green world we know now. It was hot and covered in lava, bombarded by rocks from space, completely without air as we know it. And yet, even then, the atoms were here, patient, waiting, rearranging themselves slowly, very slowly, into new combinations, new forms. Volcanoes released gases from deep inside the Earth, water vapor, carbon dioxide, nitrogen, and slowly an atmosphere began to form. Water vapor cooled and fell as rain for millions of years, filling the low places of the rocky surface until the first oceans appeared. Dark, warm, quietly shifting under a sky still full of volcanic haze. In those warm early oceans, something extraordinary began to happen. Certain molecules made of carbon and hydrogen and oxygen and nitrogen, the same atoms forged in stars, began to link together in longer and longer chains. They began to fold into shapes that could do things, react with other molecules, break apart, and reform. Some of them began to make copies of themselves. Life, when it began, was quiet. A few molecules learning to replicate in a warm, dark sea. No sound, no color, no movement visible to any eye. Just chemistry, slow, patient, ancient chemistry, finding its way, one tiny step at a time. Those first living molecules eventually became cells, and those cells, over hundreds of millions of years, became everything alive on Earth. Every tree and fish and bee and flower, every sleeping animal curled in its den tonight. And you, breathing here softly in the dark, you are made of atoms that were forged in stars. You are, in the most literal and beautiful sense, part of the universe looking at itself. Let that thought settle over you like a warm, heavy blanket. Let it soften your breathing. You don't need to hold on to it tightly. Just let it be here with you, gently, as you rest. The carbon in your body has had so many lives before this one. Not lives in the way we think of them, not with memories or feeling, but lives as a piece of the world, changing slowly from one form to another, wandering through the ages in different disguises, Right now, inside you, there are carbon atoms that may have once been part of a leaf in a forest that no longer exists. Before that, they may have been dissolved in an ancient sea. Before that, they may have floated as carbon dioxide in the air above a world where strange creatures moved through shallow swamps. Before that, much further back, they were part of a star. Carbon is one of the most social elements in the universe. It loves to bond with other atoms. It can form 4 connections at once, which makes it uniquely suited to building complicated structures. Long chains, rings, branching networks. Carbon is the architect of all living things. Every protein in your muscles, every strand of DNA in every cell, every molecule your brain uses to think and feel and dream, built on carbon. Oxygen is close behind. There is oxygen in the water you drink, in the air you breathe, in the bones that hold you gently together as you lie here. Oxygen atoms tend to travel in pairs. 2 oxygen atoms linked arm in arm, drifting through the air until your lungs draw them in and separate them gently, sending them through your blood to every cell in your body. The iron in your blood is perhaps the most poetic of all. Iron is only made in the cores of massive stars and only scattered into space when those stars explode. The iron in your hemoglobin, the molecule that carries oxygen in your red blood cells, was once inside a star. It traveled through space for billions of years before ending up here in you, in the quiet dark, helping you breathe. Right now, as you breathe slowly in and out, your blood is doing something beautiful. Every time you inhale, oxygen enters your lungs and moves into your blood. There, each oxygen molecule attaches to a molecule of hemoglobin, which contains iron at its center. The iron holds the oxygen like a hand holding something precious and carries it deep into your body, all the way to cells that need it to release energy. Then it lets go. The cell breathes in its own tiny way, and your blood returns, ready to do it again. This has been happening since before you were born, since before your parents were born, since before any human ever walked the earth. The same process, the same iron, the same quiet exchange, inherited through all the generations, all the way back to the first cells that ever learned to use oxygen. The nitrogen in your body came from the air. Most of the air around you, about 78%, is nitrogen, drifting in invisible pairs through every room, every garden, every quiet night sky. Plants take nitrogen from the soil where it arrives through the work of tiny bacteria. Animals eat the plants. We eat the animals or the plants. And the nitrogen becomes part of us. Nitrogen is in every amino acid in your body. Amino acids are the building blocks of proteins, and proteins do almost everything. They form your muscles and your skin and your hair. They carry signals through your blood. They speed up the chemistry happening in every cell. Without nitrogen, none of this could exist. Calcium is in your bones. Every bone in your body, your gentle, quiet, patient skeleton, is built largely from calcium phosphate, a mineral compound that makes bone hard and resilient. The calcium in your bones might have once been in the ocean, dissolved in ancient seawater, or locked in a limestone rock that slowly dissolved over centuries in rainwater, or part of the shell of a creature that lived and died in a warm Cretaceous sea. Phosphorus is there too, alongside calcium in your bones, and also in your DNA. The backbone of every strand of DNA, those famous twisted ladders that carry all your genetic information, is made partly of phosphate, a molecule built around phosphorus and oxygen. Every time a cell divides and copies its DNA, phosphorus atoms help carry the instructions from one generation to the next. Sulfur is in your proteins and in your skin. It is why garlic and onions have their sharp, pungent smell, compounds built around sulfur. It is why hot springs smell of rotten eggs, hydrogen sulfide gas rising from deep underground where ancient chemical reactions still take place. The sulfur in your body has likely traveled through volcanic rock, through ocean water, through soils, through plants, before arriving here. Magnesium is inside every cell. It helps your muscles relax after they contract. Without magnesium, muscles could not let go. It is also at the center of every chlorophyll molecule in every green plant. Chlorophyll, the molecule that captures sunlight and uses it to make sugar from carbon dioxide and water. In a sense, the magnesium that helps your muscles rest also helped build the plants that feed you. Potassium moves in and out of your nerve cells whenever you have a thought, feel a sensation, or move a muscle. The signals that carry sensations and thoughts and movements along your nerves are electrical, and they are powered by ions, charged atoms, moving across membranes. Potassium is one of the most important. Right now, as you lie here growing sleepy, potassium is gently flowing, signal by soft signal, along nerves that are slowing, quieting, settling toward rest. Sodium works alongside potassium. Together they create the electrical gradients that make nerve signals possible. The sodium in your body is also in the ocean. Seawater contains sodium chloride, salt, in concentrations not so different from the fluids inside our cells. Some scientists think this reflects the fact that life began in the sea, and our cells still carry a kind of memory of it. Zinc is in more than 300 of your body's enzymes, the molecules that help chemical reactions happen. Without zinc, your immune system could not fight infections, wounds could not heal properly, and your senses of taste and smell would fade. Zinc is found in oysters, in pumpkin seeds, in the dark soil of gardens, in river sediments, in rocks. It has been cycling through the Earth's crust and oceans and living things for billions of years. Copper carries oxygen in the blood of some animals, the way iron does in yours. The blood of an octopus is blue, not red, because it uses copper rather than iron in its oxygen-carrying molecule. You have copper too, though in smaller amounts, in enzymes that help your cells use oxygen properly and build connective tissue. The copper in your body may once have been in an ancient copper ore deposit, slowly dissolving over geological time. Every atom in your body arrived through some long, winding path. None of them began with you. All of them will continue after you, passed on to other forms, other places, other lives. Tonight, they are gathered here in this exact combination that makes you you, breathing, resting, warm. If you feel like leaving a like on this video or dropping a comment about your favorite part of the cosmos, that would make tonight's journey even lovelier. But for now, just breathe. You are exactly where you need to be. Our sun is a middle-aged star. It formed about 4.5 billion years ago, and it will burn for roughly another 5 billion years before it slowly expands and fades. In cosmic terms, it is unhurried, steady, reliable. Every day it rises and crosses the sky with quiet faithfulness, warming the ground, drawing water upward into clouds, coaxing seeds out of the dark soil. The sun burns through nuclear fusion, the same process that all stars use. Every second, it fuses about 600 million tons of hydrogen into helium. That sounds enormous, and it is, but the sun is so vast that it has been doing this for billions of years and will continue for billions more. The energy released by that fusion travels outward through the sun's dense interior, bouncing and scattering for tens of thousands of years before finally reaching the surface and being released as light. That means the light touching your face on a summer afternoon began its journey deep inside the sun, perhaps 100,000 years ago, when our ancestors were painting caves and walking across vast grasslands. The sunlight is not new. It is ancient, patient, finally arriving. When sunlight reaches Earth, it carries energy across all wavelengths: visible light, infrared warmth, ultraviolet rays. Plants are extraordinarily good at capturing the visible light wavelengths. In every green leaf, thousands of chloroplasts sit like tiny solar panels, gathering light and using it to pull carbon atoms out of the air and build sugar. Glucose, a simple sugar made of carbon, hydrogen, and oxygen, is the food that powers almost all life on Earth. A tree in a forest is, in a sense, made of air. The wood, the bark, the leaves, mostly carbon, captured from carbon dioxide in the atmosphere by the quiet work of photosynthesis. When you sit beneath a tree and rest against its bark, you are resting against centuries of captured sunlight. The tree is a record of all the light that fell on that spot, year after year. The oxygen you are breathing right now was made by plants and algae, exhaled as a byproduct of photosynthesis, the way we exhale carbon dioxide. For the first 2 billion years of Earth's history, there was almost no free oxygen in the atmosphere. Then, tiny ocean-dwelling bacteria called cyanobacteria began photosynthesizing in vast numbers, and gradually, over hundreds of millions of years, they filled the atmosphere with oxygen. This is called the Great Oxygenation Event, and it was perhaps the most transformative thing that ever happened on this planet. The oxygen in your lungs, filling you gently with each breath, was made by life. Billions of generations of plants and algae, from ancient blue-green bacteria to the great forests of today, have been building and maintaining this atmosphere for you, for all of us, for longer than we can quite imagine. Stars older than our sun scattered their atoms into space long before Earth existed. Some of those atoms became part of the cloud of gas and dust from which our solar system formed. So, the atoms in your body are not only from one star, they are from many stars, a collection of ancestors spread across time and space, all gathering together in you. Astronomers can tell which stars are old by looking at their composition. The very first stars, called Population 3 stars, contained almost no elements heavier than helium. They were pure and simple. Later stars, formed from the enriched leftovers of those first explosions, contained more heavy elements. Our sun is a population 1 star, rich in heavy elements, which is why planets like Earth could form around it. There were enough heavier atoms to build rocky worlds. Every rocky planet is a child of dead stars. The iron in Earth's core, the silicon in its rocks, the oxygen in its water, all synthesized in stellar furnaces and scattered by stellar explosions. Earth is not an isolated thing. It is a piece of the galaxy, temporarily assembled into a world. Meteorites, small rocks that fall from space, sometimes contain grains of material older than the solar system. These Pre-solar grains came from other stars, long dead, and somehow survived the formation of the solar system and came to rest in the rock that eventually fell to Earth. Holding a meteorite is holding something that predates the sun. It is perhaps the oldest material a human hand has ever touched. Water is another traveler. Most of Earth's water may have arrived on comets and asteroids in the early solar system, icy visitors that crashed into the young Earth and melted into the first oceans. Water molecules are simple, 2 hydrogen atoms and 1 oxygen atom, but their simplicity conceals an extraordinary talent for supporting life. Water is a solvent that can carry dissolved nutrients and minerals. It moderates temperature. It participates in chemical reactions. It fills your cells, your blood, your tears, your breath on a cold morning. The hydrogen in water is the oldest of all. Hydrogen formed in the Big Bang itself, within the first 3 minutes of the universe's existence. The hydrogen in the water in your cells has been hydrogen for almost 14 billion years. It has simply been part of different molecules, different substances, different living things over all that time. When you look at a glass of water, you're looking at something that contains atoms from the very beginning of everything. The hydrogen is Big Bang hydrogen. The oxygen is stellar hydrogen fused in a star's core. Together, they make water, and water makes you mostly what you are. Your body is about 60% water by weight. The water in you is in constant exchange with the world. You breathe out water vapor, you drink it, sweat it, cry it. Every few weeks, the water molecules in your body are largely replaced. The water cycling through you today will someday be rain or ocean or part of a cloud drifting over a mountain range. Nothing is lost. Everything returns. Breathe in. Your lungs fill gently, and somewhere in that air, old oxygen and ancient hydrogen are meeting your blood and becoming, for a moment, part of you. Breathe out, and the universe exhales with you. There is a kind of quiet wonder in the night sky that is easy to forget when you are inside, warm, with your eyes closed. But let your imagination go there for a moment, to a dark field far from any town, where the sky above is so thick with stars that you can see the faint, hazy glow of the Milky Way arching overhead like a river of light. Our galaxy contains something like 200 billion stars. Some are young and hot and blue-white, burning intensely and briefly. Some are old and cool and red, smoldering slowly. Most are somewhere in between, yellow and orange and white, burning quietly for billions of years. Each one is a furnace. Each one is making elements. The closest star to our sun is Proxima Centauri, about 4 light years away. Light travels at 300,000 kilometers per second, and even at that speed, it takes 4 years to cross that distance. When you look at Proxima Centauri on a night from the southern hemisphere, where it is visible, you are seeing light that left it 4 years ago. You are looking into the past. More distant stars show you deeper into the past. Some of the stars visible to the naked eye are hundreds or thousands of light years away. The light reaching your eye tonight left those stars when empires rose and fell on Earth, when forests grew and rivers shifted course. You are, right now, watching ancient history unfold in slow motion across the sky. Some of those distant points of light are not stars at all, but entire galaxies, each containing hundreds of billions of stars of their own. The Andromeda Galaxy, faintly visible on a clear night, is about 2.5 million light years away. The light you see from it left before any human stood upright and looked at the sky, before any stone tool was ever shaped. It left Andromeda and traveled through intergalactic space for 2.5 million years, arriving tonight in your eye if you happen to look. Stars are born in nebulae, vast clouds of gas and dust that glow in colors almost too beautiful to describe. The Orion Nebula, visible faintly as a hazy patch in the constellation Orion's Sword, is a stellar nursery about 1,344 light-years away. Inside it, right now, new stars are forming. New planetary systems may be taking shape. Perhaps some of those planets will one day carry oceans. Perhaps, billions of years from now, something will breathe their air. When a nebula is illuminated by nearby stars, it glows. Different elements emit light at different wavelengths, different colors. Hydrogen glows red, oxygen glows blue-green, sulfur glows orange. Astronomers can look at the spectrum of light from a nebula and read its composition the way you might read a recipe. They can tell, from many light years away, exactly which atoms are present. This technique, spectroscopy, also tells us that the universe everywhere is made of the same elements. The hydrogen in a distant galaxy is the same as the hydrogen in your hand. The iron in a star 50,000 light-years away is the same as the iron in your blood. The universe is one material, arranged in countless forms, but fundamentally the same everywhere. That sameness is somehow deeply comforting. There is no alien chemistry out there, no mysterious substances we cannot understand. The universe speaks one language, quietly, everywhere at once. In the hearts of dying stars, elements heavier than iron are created, but through a different process. When a massive star explodes in a supernova, the violence of that event is so extreme that elements heavier than iron can form. Gold, silver, uranium, platinum. These are literally born in explosions. The gold in any ring, any bracelet, any coin anywhere on Earth was forged in a supernova billions of years ago. Even more extreme events, the collision of two neutron stars, may produce even greater quantities of heavy elements. Neutron stars are the incredibly dense remnants of supernova explosions, crushed down to the size of a city, but with more mass than the sun. When two of them spiral together and collide in an event called a kilonova, they flash with a golden light, the signature of heavy elements being formed in real time. Astronomers detected such an event in 2017. For a brief moment, a distant point of light glowed with the synthesis of heavy elements, including gold, in quantities estimated to be greater than the mass of our entire Earth. It was, in a way, the universe making jewelry. Every gold atom that has ever existed on Earth arrived the same way. Violently, beautifully, long ago, scattered across space from some stellar catastrophe, slowly drifting and gathering until it found its way into the rock of our world. The fact that you can wear gold on your wrist or finger is just another way the universe has of ornamenting itself with its own history. Tonight, if you have a moment before sleep, you might check our playlist for more stories like this. Nights spent traveling through forests, oceans, mountains, and skies. The universe is endlessly gentle when you let it be. And right now, it is asking you to rest. Let us travel for a moment to a quiet forest at night. Imagine it, tall trees standing dark against a sky salted with stars. The air is cool and smells of pine resin and damp earth. An owl calls once, far away. Then silence. Every tree in that forest is a star child too. Every carbon atom and every fiber of wood and bark and leaf was once part of a star. The trees breathe carbon dioxide from the air. They are, in a very real sense, eating the atmosphere. And they build themselves from those carbon atoms, stacking them into long chains of cellulose, weaving them into lignin, the substance that makes wood strong and hard. A 1,000-year-old oak tree is a living record of 1,000 years of sunlight and rain and atmospheric carbon. Its roots reach down into soil built from centuries of fallen leaves and mineral-rich rock particles. The minerals in the soil, iron, magnesium, calcium, phosphorus, were once locked in rock, and before that were scattered from dying stars. In the soil itself, an entire universe of life moves quietly in the dark. A single teaspoon of forest soil contains more microorganisms than there are people on Earth. Bacteria, fungi, tiny animals like mites and springtails. All of them cycling nutrients through the soil, breaking down dead matter, releasing elements back into forms that roots can absorb. The fungi are remarkable. Many trees are connected to underground fungal networks, mycorrhizal fungi that weave their threads through the soil and link to the roots of many different trees at once. Through this network, trees can exchange sugars and nutrients. A large old tree can send sugars through the fungal network to a younger tree nearby that is struggling in the shade. Some scientists call this the wood wide web, and it transforms the forest from a collection of competing individuals into something more like a single, vast, softly breathing organism. When you walk through a forest and feel that particular kind of peace, the soft dimming of thoughts, the easing of the chest, it may partly be because forests release chemicals called phytoncides into the air. These are organic compounds that trees emit to communicate with each other and deter insects. And when humans breathe them, they lower stress hormone levels, reduce blood pressure, and boost the activity of immune cells. The forest is, in the most literal chemical sense, healing you. The peace of a forest is not imaginary. It is biochemical. It is real. The trees are sharing something of themselves with you through the air. Leaves at night are doing something different than leaves in sunlight. During the day, leaves take in carbon dioxide and release oxygen, the process of photosynthesis. At night, when there is no light, they do the reverse. They take in oxygen and release carbon dioxide, just as we do. In a way, at night, the forest breathes more like us. The colors of leaves in autumn come from the unmasking of pigments that were always present but hidden behind the green of chlorophyll. As daylight shortens and temperatures cool, trees begin to withdraw chlorophyll from their leaves, pulling the nutrients back into the branches for storage through winter. As the green fades, yellow and orange pigments, called carotenoids, become visible. Some trees also produce new red pigments called anthocyanins, the bright reds and purples of maples and sumacs, perhaps to signal insect or protect the leaf during the nutrient withdrawal process. Every leaf that falls in autumn carries nutrients back to the soil as it decomposes. The cycle completes itself, light to leaf to soil, to root to leaf again. Nothing wasted, everything returned. In a rainforest, leaves never yellow and fall en masse. The forest stays green all year, and the cycle of growth and decay happens more continuously, driven by warmth and moisture rather than seasonal change. Rainforests cover only about 6% of the Earth's land surface, but contain more than half of all plant and animal species. They are, in biological terms, the richest places on Earth. The Amazon rainforest alone produces about 20% of the world's oxygen and cycles enormous amounts of water into the atmosphere. Clouds form over the Amazon, rain falls, water soaks into the soil and is taken up by trees, transpired back into the air, and forms clouds again. The forest makes its own rain, in a sense, a vast breathing, cycling system. The trees of old forests are extraordinary reservoirs of carbon. A single large tree can hold several tons of carbon in its wood, roots, and soil. Old-growth forests, those that have never been logged, store far more carbon per acre than younger forests, because the accumulation of woody biomass and rich soil takes centuries. When you rest beneath a tree, you're resting next to something ancient and patient and full of stored light. The rings inside its trunk count the years quietly, each one a year of rain and drought, cold and warmth, all recorded in the width of a ring of wood, like a sentence in a very slow diary. Carbon is the language the universe speaks through living things. It is patient, versatile, endlessly creative. In a diamond, carbon atoms are arranged in a perfect lattice, making one of the hardest substances known. In graphite, the substance in a pencil, the same carbon atoms are arranged differently, in flat sheets that slide apart easily, leaving marks. In your DNA, carbon forms the backbone of the spiral. In the atmosphere, it floats as a gas, the same element, wearing 1,000 different faces. And all of those faces are stardust. The ocean covers about 71% of the Earth's surface. From space, our planet glows blue. Blue like no other world in our solar system. That blue is water. That water is old. That water has been here in different forms, cycling endlessly since the first rains fell on the cooling young Earth billions of years ago. The ocean is not uniform. It has layers, warm and well lit near the surface, cold and dark in the depths. Light penetrates only about 200 meters down. Beyond that, permanent darkness. But in those sunlit upper waters, an invisible forest of microscopic plants called phytoplankton grows in numbers almost beyond imagining. A single liter of seawater may contain 1 million of them. Phytoplankton are perhaps the most important organisms on Earth. They produce about half of all the oxygen in Earth's atmosphere. Every other breath you take comes from the ocean, from the quiet photosynthesis of tiny cells you will never see, drifting in sunlit water, turning light and carbon and nutrients into oxygen. They are star children too. The carbon they capture from the water was once in the atmosphere, and before that was in living things, and before that was in rock, and before all of that was in a star. When phytoplankton die, they drift downward into the dark. Some of them are eaten on the way down, and the carbon they contain is recycled in the upper ocean. But some reach the deep sea floor and settle there, forming layers of organic sediment that accumulate over millions of years. Under the right conditions, over millions more years, those sediments can be transformed into fossil fuels, the compressed remains of ancient life. The fuel that powers our cars and heats our homes is at its core ancient sunlight. It is energy that was captured by photosynthesis hundreds of millions of years ago, stored in organic molecules, buried, compressed, transformed. When we burn it, we release that ancient sunlight back into the atmosphere as carbon dioxide, returning carbon that was buried for vast stretches of time to the air that once held it. The deep ocean is cold and dark and under enormous pressure, but it is not lifeless. Creatures live down there in the permanent dark. Fish with their own bioluminescent lights, squid the size of small cars, worms and crabs and shrimp clustered around hydrothermal vents where superheated water rich in sulfur and minerals pours from the seafloor. Around those vents, entire ecosystems exist that rely not on sunlight, but on chemical energy. Sulfur oxidizing bacteria that form the base of the food chain. Life found a way even in the deepest, darkest places. The movement of the ocean is a vast, slow dance. Warm surface water near the equator flows toward the poles. As it loses heat and becomes denser, it sinks, forming deep currents that flow back toward the equator along the bottom. This circulation, called the thermohaline circulation, moves water through every ocean on a journey that can take hundreds or thousands of years. It distributes heat around the planet, moderating climates, keeping some regions warmer than they otherwise would be. Salt enters the ocean from rivers, which carry dissolved minerals from eroding rock and from hydrothermal vents. The concentration of salt in the ocean has been roughly stable for a very long time because, as fast as rivers bring salt in, minerals slowly leave, incorporated into sea creatures' shells, settled into sediment, subducted into the mantle at the edges of tectonic plates, and eventually cycled back into rock. The ocean keeps its balance over geological time. Waves are made by wind. Wind blows across the surface of the water, and friction transfers energy into the water, creating ripples that grow into waves. A wave is not the water itself moving forward. It is energy moving through water. If you watch a buoy in the open ocean, it bobs up and down as waves pass, but does not move forward. The energy passes through. The water mostly stays. When waves approach shore and the seafloor rises to meet them, the energy in the wave gets compressed. The wave slows at the bottom and rises at the top, steepening and eventually breaking. The sound of waves breaking on a shore is one of the oldest sounds on Earth, older than any animal that ever heard it. It has been happening since the first oceans existed. The sound of the sea is restful to many people, perhaps because we carry somewhere deep in our cells a memory of that ancient water. Our blood is salty like the sea. Our early embryonic development echoes stages that our distant ancestors passed through in the ocean. We are creatures of the sea in many ways, even those of us who have never seen it. Tides are caused by the gravitational pull of the moon and, to a lesser extent, the sun. The moon pulls on the ocean as it orbits the Earth, raising a bulge of water on the side facing the moon and another bulge on the opposite side. As the Earth rotates under these bulges, different shores experience high and low tides roughly twice each day. In some places, the tidal range, the difference between high and low tide, can be 15 meters or more, exposing vast stretches of mudflat at low tide and flooding them again at high. In these intertidal zones, creatures have evolved extraordinary adaptations to survive the twice-daily cycle of drowning and exposure. Mussels close their shells tight to keep moisture in. Sea anemones contract. Tide pools fill with their own small worlds. Anemones and snails and crabs and small fish, each waiting for the tide to return. If you'd like to fall asleep with more of these quiet journeys through forests, oceans, and starlit nights, Our playlist is full of them, waiting for you whenever you need to rest. And if this story has brought you some peace tonight, a little like on the video means the world to us. Rain begins far above the ground in a cloud that may have been forming all day, quietly gathering moisture from the air. Water vapor, tiny invisible molecules of water, rises from oceans and lakes and rivers, and even from the leaves of plants, lifted by the warmth of the sun. High up in the cooler air, that vapor condenses around tiny particles of dust or sea salt, forming microscopic droplets. Many millions of droplets together make a cloud. As more and more droplets form and merge, they grow heavier. Eventually they are too heavy to float, and they fall, first as the finest of mist, then as light drizzle, then as full drops of rain, each one falling through the air at a speed where wind resistance and gravity balance, reaching a steady pace of about 9 meters per second. A raindrop is not shaped like a teardrop. That is a myth. A small raindrop is nearly spherical, held in a round shape by surface tension. A larger raindrop is slightly flattened at the bottom by air resistance, like a small bun. Only in drawings and cartoons does it have that pointed top. Rain carries oxygen and nitrogen from the air. It washes dust and pollen and tiny particles from the atmosphere. By the time it reaches the ground, it is already a little bit of a soup, full of dissolved gases and particles from the air it fell through. It arrives on the ground already changed, already part of the world it is entering. The smell of rain on dry ground has a name: petrichor. It comes from oils released by plants and absorbed by dry soil, plus a compound called geosmin produced by soil bacteria. When rain hits dry soil, tiny droplets of air are trapped and then released as aerosols. And those aerosols carry the geosmin and the plant oils up into the air, where we breathe them and feel somehow that particular deep satisfaction of rain after dryness. Petrichor is one of the most widely appreciated smells on Earth across all cultures. Something in us responds to it, perhaps because rain meant survival, crops and animals, and people depending on fresh water. Perhaps because it is simply beautiful. Either way, when it rains after a long dry spell, something in you opens. Water that falls as rain soaks into the ground and begins a slow journey downward through soil and rock. Some of it is absorbed by plant roots almost immediately. Some of it reaches the water table, the underground layer of rock or soil saturated with water, and becomes part of a groundwater system that may be centuries old. Some wells draw water that fell as rain hundreds of years ago from clouds that formed over skies our ancestors looked up at. Water in rivers moves much faster. A river is the convergence of many small streams, each gathering water from the land around it. Where rain falls on a hillside, it flows in thin sheets over the ground, then gathers into rills, then streams, then rivers, carving channels as it goes, wearing rock patiently into sediment that it carries toward the sea. A river is never the same twice. It is always moving, always changing, always en route. The meandering of rivers is beautiful. Over flat land, a river does not run straight. It curves and loops, slowly moving in great bends called meanders. The outer bank of each curve is eroded. The inner bank accumulates sediment. Over time, a meander can bend so far that it cuts itself off, leaving a crescent-shaped oxbow lake, a still, quiet pool of water left behind by the river's wandering. Lakes are another kind of patient stillness. Many are filled by the same rivers that once carved the land. Some are very old. Lake Baikal in Siberia is 25 million years old, the world's oldest and deepest lake. It holds about 20% of all the world's liquid fresh water. Its cold, clear depths are home to more than 1,000 species found nowhere else on Earth, including a freshwater seal that somehow found its way there or evolved there, surrounded on all sides by land. Ice is water with its molecules arranged in a crystalline lattice, a geometric structure that makes ice slightly less dense than liquid water. This is why ice floats, which is not true of most substances when they freeze. If ice sank, the bottoms of lakes and ponds would fill with ice from the bottom up, and many lakes would freeze solid in winter, killing everything in them. Because ice floats, it forms an insulating layer on top, protecting the liquid water and the life within it from the cold above. Snowflakes are crystals of ice that form around tiny particles in clouds. Water vapor attaches to a dust particle and freezes, building outward in six-fold symmetry. Because of the geometry of water molecules, ice crystals always have 6 sides, 6 arms, six-fold symmetry. Each snowflake's unique pattern is determined by the exact conditions of temperature and humidity it passed through on its way down. 2 snowflakes traveling through slightly different paths encounter slightly different conditions and build slightly different crystals. In all the snow that has ever fallen, it is thought that no 2 snowflakes have ever been exactly alike. Each snowflake is a small, fleeting piece of the water cycle. It falls, settles, is buried under more snow, may slowly become part of a glacier, and may melt thousands of years later, joining a meltwater stream, flowing to the sea, evaporating, rising again as vapor, and someday falling once more, as rain or snow somewhere else, in some other time. Think about a stone, not a polished one, not a special one, just an ordinary stone, the kind you might pick up from a riverbank or a garden path. Gray, perhaps, or brown, slightly rough, cool to the touch. That stone is a record. Everything that has happened to it, the conditions under which it formed, the pressures it endured, the minerals that crystallized within it, all of that is written in its structure. Geologists can read stones the way some people read faces, seeing age and history and the marks of experience. Most rocks on Earth belong to one of 3 families. Igneous rocks form when molten rock, magma, or lava cools and solidifies. Granite is an igneous rock that formed deep underground, cooling slowly over millions of years, allowing large crystals to grow. Basalt is an igneous rock that formed quickly from lava cooling on the surface, with crystals too small to see without a microscope. Obsidian is volcanic glass, lava that cooled so fast that no crystals formed at all, just a smooth, glassy, dark substance used by ancient peoples to make blades. Sedimentary rocks form from layers of sediment, particles of sand, silt, clay, or the remains of living things that accumulate over time and are slowly compacted and cemented together. Limestone is often built from the shells and skeletons of sea creatures, compressed and transformed over millions of years into rock. Sandstone is ancient sand, pressed solid. Shale is ancient mud. Coal is ancient plant material. These rocks are libraries, pages of time laid one on top of another. Metamorphic rocks form when igneous or sedimentary rocks are subjected to intense heat or pressure deep in the earth or near a magma intrusion, and their minerals recrystallize into new forms. Marble is metamorphosed limestone. Slate is metamorphosed shale. Quartzite is metamorphosed sandstone. They carry within them the memory of what they once were, transformed by heat and time into something harder and more crystalline. The rock cycle has no beginning and no end. Igneous rock is eroded by wind and water into sediment, which becomes sedimentary rock, which may be buried and metamorphosed, which may be melted and become magma, which cools into igneous rock again. The process takes tens or hundreds of millions of years, but it never stops. The rocks beneath your feet are in motion on geological time. Beneath the continents and ocean floors, the Earth's tectonic plates move slowly, about as fast as your fingernails grow, but relentlessly. Where plates pull apart, magma wells up and forms new rock. The Mid-Atlantic Ridge is doing this right now, adding new seafloor between the Americas and Europe, pushing them a little further apart each year. Where plates collide, one dives beneath the other, subduction, and rocks are drawn back down into the mantle to be melted and recycled. The Himalayas are still rising, millimeter by millimeter, as the Indian plate continues to press against the Eurasian plate. Mountains are not permanent. They form through the collision of plates, rise over millions of years, and are simultaneously being worn away by erosion. The Appalachians in North America were once as tall as the Himalayas. They are among the oldest mountain ranges on Earth, and time has worn them down to gentle, rounded ridges. The Himalayas are young and sharp-edged by comparison, still rising faster than erosion can wear them down. Rivers carry the eroded material from mountains in the form of sand and silt and dissolved minerals, down to the sea, where it settles on the continental shelf and deep ocean floor, slowly building new sedimentary layers. The Mississippi River carries an estimated 500 million tons of sediment to the Gulf of Mexico every year. Imagine that. 500 million tons of mountain and plain, quietly carried to the sea. The minerals in the soil that grow your food came from rock. Nitrogen arrives through the air and through bacteria, but calcium, magnesium, phosphorus, potassium, iron, zinc, all of these come from the slow weathering of rock, particles dissolving and becoming available to plant roots. The vegetables you eat are, in a very real sense, made of mountain, and that mountain was made of stardust. Caves form when slightly acidic rainwater dissolves limestone over thousands or millions of years, creating underground chambers and passages. In some caves, the dissolved limestone redeposits as water evaporates or drips, building stalactites from the ceiling and stalagmites from the floor, centimeter by centimeter, century by century. Some cave formations are thousands of years old, still growing, still dripping. Ancient humans sheltered in caves. They painted their walls with animals and hands and symbols that we still do not fully understand. Those paintings, preserved by the stable temperature and humidity of the cave, have survived tens of thousands of years. In the Chauvet Cave in France, paintings of lions and rhinos and horses were made 36,000 years ago by people whose hands contained the same stardust atoms as yours. Their iron-rich blood dripped the same color as yours. Their carbon-built neurons fired in the dark of that cave, imagining what to paint. They looked up at the same stars you do. They felt the same smallness and wonder. and the atoms in them were, then as now, as old as the universe. Birds are extraordinary. They carry within them the inheritance of dinosaurs, literally, because birds are living dinosaurs, the direct descendants of a lineage that survived the mass extinction 66 million years ago. The feathers on a bird are the same structures that some non-avian dinosaurs also had. Flight in birds is a technology that has been refined over 150 million years. When you hear birdsong at dawn, you're hearing something ancient, a sound that echoed through forests of tree ferns and conifers when the world was very different, when the stars in the sky were the same stars, but the continents were in different positions and the climate was warmer. Birdsong has been waking mornings for millions of years. The dawn chorus, that extraordinary rush of birdsong in the minutes around sunrise, happens because birds use song to establish territory and attract mates. And the cool, still air of dawn carries sound farther than the noisy, turbulent air of midday. The stillness of early morning is the bird's amplifier. Each species of bird has its own song, a signature built into its neural circuits partly through inheritance and partly through learning. Young birds learn the specific dialect of their species from their parents, refining it through practice the way a child learns language. In some species, males far away from the center of a population develop slightly different dialects, regional accents that accumulate over generations. Hummingbirds are extraordinary stars of the bird world. They can hover in place by beating their wings 50 to 80 times per second. So fast the wings blur into a soft, vibrating hum. To fuel this, their hearts beat over 1,000 times per minute, and their metabolic rate is the highest of any bird. At night, to survive without food, they enter a state called torpor, slowing their heart rate and body temperature dramatically to save energy, almost like a nightly hibernation. Each morning, they warm up again, returning from the edge of cold stillness. The migration of birds is one of the quietest miracles of the natural world. Arctic terns fly from the Arctic to the Antarctic and back every year, a round trip of about 70,000 kilometers, the longest migration of any animal. They spend their lives in perpetual summer, always chasing the light. Their atoms, their carbon, their oxygen, their iron, trace an enormous figure 8 across the globe, year after year. Birds navigate by many means. Some use the sun tracking its position through the sky to determine direction. Some navigate by the stars, orienting themselves by the pattern of the night sky. Some, including robins and pigeons, can detect the Earth's magnetic field directly using tiny crystals of magnetite, a naturally magnetic mineral, in their tissues. They carry inside their bodies a biological compass built from iron, one of the universe's most ancient elements. The flight feather is a marvel of engineering, a shaft with hundreds of barbs, each barb bearing hundreds of barbules, each barbule bearing a tiny hooks that interlock with the barbules on neighboring barbs, forming a flat, flexible surface that can bend and return to shape. When a bird preens, it runs its beak along the feather, reconnecting any unhooked barbules, restoring the surface. The whole feather is essentially a very sophisticated zipper, maintained with care. Owls are built for silence. Their feathers have soft, comb-like edges that break up the turbulence of air flowing over the wing, eliminating the whooshing sound that other birds make in flight. Owls can fly in complete silence, invisible in darkness, audible only if they choose. The disk of feathers around an owl's face acts as a parabolic reflector, gathering sound and directing it toward the ear openings. Some owls can locate prey by sound alone in total darkness, with an accuracy of less than 1 degree. On a quiet night, an owl may perch in a tree nearby, and you would never know it was there. It sits in perfect stillness, watching with those large, forward-facing eyes, designed for seeing in very low light, with a high proportion of rod cells sensitive to dim illumination. When it finally moves, there is no warning sound. Songbirds weigh almost nothing. A tiny chickadee weighs about 10 grams, 2 nickels. And yet, it can survive temperatures of minus 30 degrees Celsius, foraging through snow for hidden seeds, shivering to generate heat, its blood sugar maintained by a tiny nervous system that tracks calorie needs with extraordinary precision. Life at such small scales is a constant negotiation with the cold, the wind, the available food. Every bird's egg is a sealed world. Everything the developing chick needs is inside, in the yolk and the albumin and the membrane. Gas exchange happens through thousands of tiny pores in the eggshell. The shell itself is built from calcium carbonate, calcium from the mother's bones, carbon from the air, oxygen from water. When the chick is ready, it uses a special tooth, the egg tooth, to chip away at the shell from the inside. It breaks open its sealed world and breathes the air of the larger one for the first time. If you enjoy these quiet journeys through the natural world, do leave a comment telling us which creature you find most wondrous. We read everyone. And now, let yourself drift a little further into rest. Insects are the most abundant animals on Earth and among the most ancient. They have been here for about 400 million years, long before the dinosaurs, long before any flower existed, long before any bird sang in any tree. They survived every mass extinction that wiped out most of the large animals. Whatever trials the world has faced, the insects have persisted. A bee visiting a flower is participating in one of the most important partnerships in the history of life. Flowering plants and bees co-evolved, each shaping the other. Flowers developed colors and shapes and scents that attracted bees. Bees developed bodies with stiff bristled pollen baskets on their hind legs and brains capable of navigating landscapes, memorizing the locations of flowers, and communicating with other bees about where to find them. The waggle dance of honeybees is one of the most elegant communication systems in the animal world. When a forager bee returns to the hive with information about a particularly good food source, she performs a figure-8 dance on the vertical face of the honeycomb. The angle of the straight part of the figure-8 indicates the direction to the food source relative to the sun. The duration of the waggle run indicates the distance. Other bees follow the dancer, reading the information, and set off in the correct direction. It is a symbolic language, encoding spatial information in movement. Carl von Frisch, who decoded the waggle dance in the 1940s, called it, with good reason, one of the most remarkable achievements of animal communication known to science. Ants live in colonies that can contain millions of individuals, and yet there is no central coordinator, no queen giving orders, no foreman directing the work. The colony's behavior emerges from the interactions of thousands of individuals following simple rules. When an ant finds food, It lays a chemical trail of pheromones on its way back to the nest. Other ants, finding the trail, follow it and reinforce it if they find food. The stronger the trail, the more ants follow it. Trails to sources that run out are not reinforced, and they evaporate. Through this simple process, ant colonies efficiently allocate workers, build complex tunnels, and transport food without any individual ant understanding the whole system. Fireflies produce their light through a chemical reaction in their abdomens, involving a molecule called luciferin and an enzyme called luciferase. The reaction produces light without heat, cold light, remarkably efficient. Different species of fireflies have different flashing patterns, different codes, used to attract mates. A meadow full of fireflies on a summer night is a landscape full of tiny conversations, each flash a word in a language written in light. Butterflies were caterpillars. Inside the chrysalis, the caterpillar's body does not simply reorganize, it largely dissolves. Most of the cells break down into a kind of biological soup from which the butterfly's body is built almost from scratch, using clusters of cells called imaginal discs that were present in the caterpillar, but inactive. The transformation is so complete that in some experiments, butterflies have demonstrated memory of experiences that happened when they were caterpillars, as though something threads through the dissolution and reconstruction. Dragonflies are ancient. Fossils of their ancestors, some with wingspans of 60 centimeters, have been found from over 300 million years ago. Modern dragonflies are among the most capable flyers in the insect world. They can fly forward, backward, sideways, and hover in place. They can change the angle of each of their four wings independently, giving them extraordinary maneuverability. And they are extraordinarily successful hunters, catching their prey in the air over 90% of the time, one of the highest success rates of any predator. Silkworms spin silk, a protein fiber produced in glands in their bodies. A single silkworm can produce a thread of silk up to 1,500 meters long during the process of spinning its cocoon. Humans have been cultivating silkworms and harvesting silk for at least 5,000 years, and the Silk Road, those ancient trade routes connecting Asia, the Middle East, and Europe, took its name from this small creature's thread. Beetles make up about 40% of all insect species, and insects are about 80% of all animal species. This means roughly a third of all animal species on Earth are beetles. When the biologist J.B.S. Haldane was asked by a theologian what studying nature had revealed about the mind of God, he reportedly replied that God had an inordinate fondness for beetles. The actual variety is staggering, from tiny bark beetles barely visible to the eye, to rhinoceros beetles the size of a fist, to the bombardier beetle, which can fire a boiling chemical spray from its abdomen in rapid pulses with an audible popping sound. A caterpillar's entire world is a leaf. It hatches, eats, sleeps, eats, sleeps. It does not need to know about stars or oceans or the origin of elements. Its atoms, assembled from the leaf and the air, are building something that will one day float on different currents, visit flowers, catch the light. For now, it simply eats and rests. The sun rises every morning in an eastern sky and travels a slow arc toward the west. In every language ever spoken, the sun has had a name, because life here has always been shaped by it, always organized around its rhythm. Animals and plants have internal clocks synchronized to the 24-hour cycle of light and dark. Your own body keeps time, temperature, alertness, hormone levels, appetite, all rise and fall in a daily rhythm driven by light. Sunrises carry a particular quality of light. When the sun is near the horizon, its light travels through a much thicker slice of atmosphere to reach you than when it is overhead. The blue wavelengths scatter out of the beam over that long journey, leaving mostly the longer wavelengths, reds, oranges, yellows, to arrive at your eye. This is why sunrises and sunsets are warm in color, while the midday sky is blue. That scattering of blue light, called Rayleigh scattering, after the physicist who described it, is also why the daytime sky is blue. Sunlight is white, a mixture of all wavelengths. But as it enters the atmosphere, blue light is scattered in all directions by air molecules. Blue arrives at your eyes from every direction in the sky, so the whole sky looks blue. Above the atmosphere, in space, the sky is black. On a day with high clouds, the light is diffuse and soft, scattered in many directions by ice crystals before reaching the ground. Shadows are soft. Colors are gentle. This is the light that painters often prefer. Not the high contrast of direct sun, but the even, luminous quality of an overcast day. The sun's light takes about 8 minutes and 20 seconds to travel from the sun to the earth. If the sun were suddenly to go dark, we would not know for 8 minutes and 20 seconds. We would still see it shining in the sky, the last light already on its way. The delay of distance making the universe seem slightly less immediate than it is. The warmth you feel on your face in sunlight is primarily infrared radiation, a form of light just longer in wavelength than the visible red, which we feel as heat rather than see. The infrared warms the surface of your skin, which in turn warms the blood beneath, which carries that warmth through your body. The sun's warmth is nuclear energy converted to light in the sun's core, traveling 8 minutes through space and arriving as warmth in your skin. Plants track the sun. Many flowers open in the morning and close at night. Some, like sunflowers when young, actually face east in the morning and slowly turn to face west through the day, tracking the sun's position to maximize light absorption. This movement, called heliotropism, is driven by unequal growth on different sides of the stem. The shadowed side grows faster, bending the stem toward the light. At night, they turn back to face east again, ready for the next morning. Trees also respond to light. In a forest, competition for sunlight shapes everything. The tallest trees command the most light. Smaller trees below them must wait or find gaps, openings in the canopy created when a tall tree falls, to push upward. A young tree in deep shade may barely grow for decades, waiting patiently in low light, building just enough reserves to survive. When a gap opens, it can suddenly shoot upward, years of growth compressed into a few seasons of bright light. Shadows have texture. Under a deciduous tree in summer, sunlight filters through thousands of leaves, creating a shifting, dappled pattern on the ground. Coins of light moving with the wind, overlapping, brightening, dimming. Each circle of light is a tiny image of the sun, formed by the natural lens effect of small gaps between the leaves. During a solar eclipse, these circles take on the shape of the crescent sun, thousands of tiny crescents dancing on the ground. The quality of light changes through the day. Morning light is low and golden, casting long shadows, making every object three-dimensional and warm. Midday light is harsh from directly above, flattening forms, bleaching color. Evening light returns to warmth, lower and softer, making the world glow. At sunset, the sky moves through colors quickly, first pale yellow, then orange, then deepening red, then a brief and extraordinary moment when the sky near the sun glows deep salmon and the zenith fades through violet. After the sun drops below the horizon, there is sometimes a belt of blue shadow on the opposite horizon, Earth's own shadow cast upward into the atmosphere. For a few minutes, you can see, if you look, the shadow of the whole planet. And then, night. Night is not the absence of everything. It is the presence of different things. The sounds change. Crickets and frogs take the place of birds. The wind settles, and sounds carry differently in the cool, still air. The light changes, the hard edges of daylight dissolve, and the world becomes softer, more continuous, more whole. Stars appear gradually as the sky darkens. First, the brightest, then more and more, until on a clear night, far from city lights, the sky is a crowded, intimate sea of points of light. The human eye can see about 5,000 stars under perfect conditions. But even that number gives a false impression of the galaxy's scale. On a clear night, you are seeing only the nearest stars, mostly within a few thousand light years. The vast majority of the galaxy's 200 billion stars are hidden in the haze of distance. The Milky Way is the disk of the galaxy seen edge-on from inside. We are about 2/3 of the way from the center of the galaxy to its edge, orbiting the galactic center at about 800,000 kilometers per hour. Though you feel no sense of motion, we complete one orbit of the galaxy about every 230 million years. The last time Earth was in this position in its galactic orbit, dinosaurs were just beginning to emerge. Everything in the galaxy orbits the center. Near the center is a supermassive black hole, an object with a mass about 4 million times that of our sun, compressed into a region smaller than our solar system. Around it, stars orbit at extraordinary speeds, some completing their orbit in just years. The black hole itself, called Sagittarius, a star, is not something you can point to easily in the sky. It is in the direction of the constellation Sagittarius, hidden behind clouds of interstellar dust. A black hole is not a hole. It is an object, an extremely dense concentration of mass, with gravity so strong that not even light can escape if it gets too close. The boundary at which escape becomes impossible is called the event horizon. Anything crossing the event horizon is, from the outside universe's perspective, gone forever. But on the inside, if the mathematics holds, time and space are distorted in extreme ways that we cannot currently observe. Around many black holes, gas and dust spiral inward in an accretion disk, heated by friction and compression until it glows, sometimes outshining entire galaxies. These are quasars, and some of the most distant objects we can see in the universe are quasars, blazing from billions of light years away, the light of matter falling into an abyss. Neutron stars, the remnants of some supernovae, are almost incomprehensibly dense. A single teaspoon of neutron star material would weigh about 1 billion tons. They spin rapidly, some thousands of times per second, and emit beams of radiation from their magnetic poles. When those beams happen to sweep past Earth with each rotation, we detect regular pulses of radio waves. We call these objects pulsars. The first pulsar was discovered in 1967, and for a brief moment, astronomers considered the possibility that the perfectly regular signal was artificial, a transmission. They tentatively named it LGM-1 for Little Green Men. It was, of course, a rotating neutron star, but the impulse to wonder was reasonable. The universe is about 13.8 billion years old. The Earth is about 4.5 billion years old. Life appeared on Earth roughly 3.5 to 4 billion years ago. Complex, multicellular life is much more recent, about 600 million years. Dinosaurs lasted about 165 million years. Modern humans, Homo sapiens, have existed for perhaps 300,000 years. The span of recorded human history is about 5,000 years. In cosmic terms, we are extraordinarily new. The universe was already 10 billion years old when our solar system formed. It had been making and exploding stars, forging and scattering elements, building galaxies for longer than the current age of the Earth, before any of the atoms in our planet existed in the form they are in now. And yet, here we are, assembled from that ancient material, briefly alive, aware, lying in the dark, looking up at a sky full of the furnaces that made us. This awareness, this ability to look at the night sky and understand even a little what it is, seems like one of the most extraordinary things the universe has produced. Not because it is practically useful, but because it is beautiful. The universe spent billions of years making the atoms that make the brains that can contemplate the universe. There is something quietly wonderful about that loop. If this story has given you a moment of peace tonight, we would love it if you left a comment or a like. It helps more people find the quiet corner of the internet we've made together here. And we have more journeys waiting for you in the playlist whenever you need them. Grass is everywhere. It is so common that we often stop seeing it. It becomes a background, a texture, something to walk over on the way to something else. But grass is extraordinary. It is among the most successful plants that have ever lived, covering about 40% of the Earth's non-polar land surface, growing on every continent, thriving in conditions that would kill most other plants. What makes grass so resilient is partly its growth habit. Most plants grow from their tips. Damage the tip of a branch or leaf, and you damage the growing point, setting the plant back. But grass grows from the base of the leaf. The meristem is low to the ground, protected. Graze it, trample it, cut it, and the growing base is still there, still alive, still ready to push new cells upward. It is stubborn in the most peaceful and gentle way. A meadow in summer contains more life per square meter than almost any other habitat in a temperate climate. But much of it is invisible. Beneath the grass, roots form an intricate web, threading through the top layer of soil, binding it together, preventing erosion, exchanging nutrients with fungi. At the surface, insects of hundreds of species move through the stems. Spiders build webs between grass blades. Beetles move through the thatch. Voles and mice tunnel beneath. Larks and pipits nest in small cups hidden among the stems. Grains are grasses: wheat, rice, barley, maize, oats, rye, millet, sorghum. All of the world's major grain crops are members of the grass family, Poaceae. The civilization of most of the world was built on grain, the ability to store concentrated food energy in the form of starchy seeds through the winter or dry season. the Fertile Crescent of the Middle East, where agriculture began about 10,000 years ago, was fertile in large part because it was covered with wild grasses whose seeds could be harvested and stored. Wheat contains gluten, a network of proteins that forms when flour is mixed with water and kneaded. This network traps the carbon dioxide bubbles produced by yeast, allowing bread to rise. The making of bread, so ordinary, so ancient, so central to so many cultures, is a form of harnessing the carbon cycle. Wheat captures CO2 from the air. Yeast converts the grain sugars into CO2. The CO2 lifts the dough. Heat transforms it into bread. Eating the bread, your body releases the energy stored in those carbon bonds. The carbon exhaled in your breath will someday be captured by another plant. Bamboo is a grass, the largest member of the grass family. It can grow up to 90 centimeters in a single day, making it the fastest growing plant on Earth. Some bamboo species flower only once every 120 years, then die. All the plants of the same species flowering simultaneously across thousands of kilometers, regardless of location. The mechanism behind this synchrony is not fully understood. The bamboo has been counting, somehow, keeping time over a century. And when the moment comes, it flowers, seeds, and ends. Moss is among the oldest of land plants. Mosses appeared on land roughly 470 million years ago, before any trees, before any insects, before any animal had set foot on dry earth. They have no roots. They anchor themselves with structures called rhizoids and absorb water directly through their leaves. A patch of moss can dry out completely in drought, shrinking and darkening, appearing dead. And then, with the return of rain, rehydrate and resume photosynthesis within hours. In a forest, after rain, moss glows, luminous green, almost impossibly vivid against the dark bark and soil. It holds moisture in the forest floor, creating microhabitats for tiny creatures. It softens sound. Kneeling to touch it, you touch something very old, a body plan that has worked continuously for nearly 500 million years. Lichens are not one organism but two, a fungus and an alga, or cyanobacterium, living together so closely that they function as a single entity. The fungus provides structure and water retention. The alga provides photosynthesis. Together, they can colonize bare rock where almost nothing else can live, secreting weak acids that slowly etch the rock surface, beginning the slow process of soil formation. Some lichens grow so slowly, just a millimeter or less per year, that a lichen patch the size of your palm might be hundreds of years old. Ferns predate flowering plants by a vast margin. Tree ferns grew in forests before the first dinosaurs appeared. Modern ferns are the survivors of that ancient world, still reproducing by spores rather than seeds, still following a growth pattern established hundreds of millions of years ago. The young fronds emerging tightly coiled, uncurling as they grow in a gesture of slow unfolding. A field of wild flowers in bloom, poppies and clover and oxeye daisies in summer, contains, in the genetic information of each plant, an archive of all the evolutionary pressures and environments that shaped its lineage over millions of years. Each flower's form is the answer to millions of years of questions. What shape attracts pollinators? What color? What timing? What scent? What depth of nectar? The flower is an evolutionary poem written in pigment and form. Wind moves through the world invisibly, making itself known by what it touches. You can feel wind before you see it, the lift of hair, the cool on the back of a hand. And a moment later, the grass bends, the leaves turn pale as their undersides catch the light, and the world shows you what the air is doing. Air is mostly nitrogen, about 78%, with oxygen at about 21%, and the remaining 1% a mixture of argon and trace gases, including carbon dioxide. This atmosphere extends from the ground upward about 100 kilometers, though 99% of its mass is in the lowest 30 kilometers. Above that, the atmosphere thins gradually into the vacuum of space. No sharp edge, just a slow fading. Pressure moves air. Where the sun heats the surface of the earth, the air above it warms and rises. Cooler air flows in from nearby areas to replace it, creating wind. At the scale of the whole planet, this creates great systems, the trade winds, the westerlies, the polar jet streams, all driven ultimately by the difference in solar heating between equator and poles, shaped and deflected by the Earth's rotation. On a summer afternoon, a sea breeze develops along the coast. The land heats more quickly than the water. Air over the land warms and rises. Air over the sea is cooler and denser and flows in to replace it, bringing the smell of salt and the coolness of the water. Then, at night, the land cools faster than the sea and the breeze reverses. The coast breathes in and out daily, following the sun. Air carries seeds. Dandelion seeds float on feathery parachutes, a structure of fine filaments attached to the seed at the center, held open like an umbrella by the shape of the fiber. In a gentle breeze, they can travel hundreds of meters. Some seeds are carried by stronger winds much further. The spores of ferns and mosses, lighter and smaller, can travel thousands of kilometers. Life uses the air as a highway. A breath of wind in a pine forest carries terpenes, aromatic organic compounds released by the resin of the trees. These are the molecules responsible for the characteristic smell of a pine forest. Clean, sharp, resinous, with something slightly sweet underneath. Terpenes are also produced by many other plants, and together with other plant-released compounds, they form part of the aerosol that hangs invisibly in forest air, the blue haze visible over mountain forests on warm days. Mountain weather changes fast. A clear morning can become a thunderstorm by afternoon. As air rises over a mountain, it cools, and cool air holds less moisture. Clouds form where the rising air cools below the dew point. On the windward side of a mountain range, rain falls heavily as wet air rises and cools. On the leeward side, the air descends and warms, and the climate is much drier. A rain-shadowed desert. Thunder comes from lightning. A lightning bolt superheats the air along its channel to about 30,000 Kelvin, about 5 times the surface temperature of the sun. This superheated air expands explosively, faster than the speed of sound, creating the shock wave we hear as thunder. Because light travels almost instantaneously and sound travels about 1 kilometer every 3 seconds, the gap between the flash and the thunder tells you how far away the lightning struck. Wind erodes rock. Over geological time, wind-blown sand sculpts stone into shapes that seem impossible: arches, towers, balanced rocks, fluted canyons. In desert regions, sand grains carried by wind grind against rock surfaces with a persistence that has no other equal. Each grain impacts the rock with a tiny force, but there are so many grains over so many years that whole cliff faces are polished smooth or carved into undulating forms. The wind carries memory in its molecules. The air you are breathing has circulated through the atmosphere many times. Some of the molecules in your lungs right now have been breathed before by other people, other animals, over all the centuries that life has been breathing on this planet. The oxygen in one breath was exhaled by a plant somewhere in the last few thousand years. Some of the carbon dioxide you are exhaling will be absorbed by a plant on the other side of the world. The atmosphere is a commons shared by all breathing things all the time. The atmosphere protects. It absorbs much of the sun's harmful ultraviolet radiation in the ozone layer, high in the stratosphere. It burns up most of the small rocks that fall toward Earth from space. It moderates temperature without the greenhouse effect, which traps some of the sun's heat. The average temperature of Earth's surface would be about minus 18 degrees Celsius, far too cold for liquid water. The atmosphere, in its quiet presence, makes everything possible. There is something lovely about the way the universe works without asking anything of you. Right now, while you lie still, electrons are moving in their paths around the nuclei of your atoms. Chemical reactions are happening in your cells, millions of them per second, in perfect coordination. Your heart is squeezing and releasing in its ancient rhythm. Your neurons are carrying soft electrical signals from one place to another, processing the quiet information of rest. Your liver is doing its patient, complex work. Your kidneys are filtering. Your skin is maintaining itself. Your immune system is gently patrolling. All of this without any instruction from you. All of this happening in the warm darkness of your body, independently, faithfully, because it has been happening this way for as long as you have been alive. You do not run your body runs itself. You are hosted by a system so complex and so capable that the best scientists in the world have spent lifetimes studying it and still have not reached the end of its depths. An atom is almost entirely empty space. If you took the nucleus of a hydrogen atom and made it the size of a marble, the electron that orbits it would be about a mile away. Everything between them, all that space, is not nothing exactly, but it contains no solid matter, just forces, just fields, just the invisible structure that holds everything in its arrangement. So, when you think about how solid your body feels, warm and real and present, the weight of it on the bed, the warmth of the blankets, it is remarkable. All of that solidity comes from the electromagnetic forces between atoms, from the energy that holds the whole structure together. You are not dense matter. You are a pattern, a beautiful, self-sustaining, breathing pattern made of mostly empty space, held in shape by forces older than the earth. And that pattern is made of stardust. The oxygen atom in your body is the same oxygen atom that once existed inside a star. Nothing has changed about it in all those billions of years. It has been in many places, taken many forms. It has been part of gas clouds and comets and ancient seas and the bodies of creatures that lived and died long before the first humans. But the atom itself, its essential nature, the number of protons in its nucleus, the way it interacts with the world, that has not changed. It does not know whether it is in a star, or a cloud of gas, or a lungful of air, or a sleeping human body. It simply is. It exists, as it always has, in whatever form the universe currently has it. And you simply are, too, right now, just existing, just breathing, just being a temporary arrangement of very ancient matter. You don't have to be anything more than that tonight. You don't have to accomplish anything or understand anything or be anywhere. You are just matter, resting, and that is enough. The world outside might be full of noise and urgency, full of things to do and places to be. But in here, in this quiet, you are just atoms, arranged in the shape of a person resting on the surface of a planet in the dark. Let us drift now toward water. Water is everywhere on Earth, in the oceans, in the clouds, in the rivers and lakes and morning dew, in the soft mud at the edge of a pond, in the veins of every leaf. The sound of water is one of the oldest sounds in the world. Rain on leaves, a river over stones, the long, slow movement of waves. These sounds have been here for billions of years, long before there were ears to hear them. Your body is mostly water. About 60% of you, more or less, is this simple, quiet molecule. 2 hydrogen atoms and 1 oxygen atom held together. Nothing simpler, nothing more essential. Water is the medium in which everything in your body happens. The solvent that carries nutrients and signals and waste. The substance that fills your cells. The moisture in your eyes and your breath. Hydrogen is the oldest element. It was born in the first minutes after the beginning of the universe, in that original rushing heat before any stars existed. In those early moments, when the universe was still a hot, dense place, protons formed, and protons in their simplest state, surrounded by 1 electron, are hydrogen. The hydrogen in your water, in the water in your cells, in your blood, in the soft tissue of your eyes. That hydrogen has been hydrogen since nearly the beginning of everything. It has never been anything else. It did not need a star to make it. It arrived first, before the stars, before the planets, before anything. And it waited in the form of gas clouds for billions of years until the universe was ready for the next steps. So, when you drink a glass of water, or when you feel the cool softness of water on your skin, you're touching something that is nearly 14 billion years old. The same hydrogen, the same quiet, ancient atom, moving through your body right now, carrying things, dissolving things, being part of the chemistry of your life. And the oxygen in that water, that newer stellar oxygen made in the heart of a star, joined with the hydrogen at some point, perhaps when the Earth was young and the oceans were still forming. Scientists believe that a significant portion of Earth's water was delivered by comets and asteroids, icy travelers that came from the outer solar system and crashed into the young Earth, bringing their frozen cargo with them. The oceans fell from the sky, in a sense, piece by piece, over hundreds of millions of years. The ocean, that vast and ancient body of water that breathes slowly with its tides, is partly made of ice that fell from the sky billions of years ago. Ice that was once comet. Before that, ice that formed from hydrogen and oxygen drifting together in the cold of deep space. Before that, hydrogen from the very beginning of the universe, and oxygen from the death of a star. And that ocean's water has moved through the world for a very long time. It has been frozen in glaciers, evaporated into clouds, fallen as rain on prehistoric forests, run in rivers that no longer exist, seeped through stone and risen in springs. It has been breathed and drunk and sweated and cried, by every living thing that has ever existed on this planet. And some of it is now in you. You are ocean too, ancient ocean, ancient ice, ancient hydrogen, ancient stars. All of it here, in the soft weight of your body, in the warmth of you. Let yourself feel the weight of your body, heavy and still, like water in a deep lake, undisturbed, settled, at rest. There is a kind of knowledge that you can carry lightly, like a stone in a pocket that you forget about until you reach in and feel it there, smooth and cool and solid. You're not always thinking about it, but it's there, and when you find it, there is a small, good feeling of recognition. The knowledge that you are made of stars is like that. You don't need to think about it constantly. You don't need to do anything with it. It's just there, warm and real, whenever you want to reach for it. Right now, if you brought your hand to your face and breathed on it, that soft breath, that small cloud of warmth, you would be breathing out carbon dioxide, carbon and oxygen, both made in stars, returning to the air from your lungs, which are themselves made of stardust. You are giving back, in this small, quiet moment, what the universe once gave you. Somewhere, a plant will take that carbon dioxide in. It will use the energy of sunlight from our own middle-aged star, our sun, to break apart that molecule and keep the carbon. That carbon will become part of a leaf, and the leaf will fall in autumn and become part of the soil. And something will grow from the soil, and something will eat what grew. And perhaps, in a very long and roundabout way, some of that carbon will find its way back into a person, into a sleeping child perhaps, or a quiet animal curled in the dark. This cycle has no beginning and no end. It has been running continuously for billions of years. Atoms moving through the world from form to form, never created, never destroyed, only rearranged, only passed along. The water you drank today has been through rain clouds and rivers and the bodies of plants and animals and the ancient ocean. The air you breathe has been breathed before by every kind of creature that has ever lived. The ground beneath this building was once the bottom of a sea, or the surface of a plain, or the inside of a mountain range, worn down by wind and water over millions of years. Everything returns, everything circles, nothing is lost. This is one of the most comforting things about the universe, if you sit with it. Matter does not disappear, energy does not disappear. The atoms in you have always existed and will always exist. They will simply move on after you into other forms, into soil, into water, into air, into other living things. Your atoms will have more adventures after you. But right now, in this moment, they are here, they are you, and you, right now, are a small and beautiful part of a very large and very old story. One that does not end with you, one that was going long before you and will go long after, quietly, patiently, in the way that the universe always has. If you are watching this as part of your nighttime routine, please check out the playlist. There are so many quiet journeys there, waiting whenever you need them. Let your body be heavy. Let your breath be slow. Let's think about nitrogen for a little while. Nitrogen is an element you might not think about often, but it is essential to life in a deep and beautiful way. 78% of the air around you right now is nitrogen. When you breathe in, most of what enters your lungs is nitrogen, which then comes back out on the exhale. Your body does not use atmospheric nitrogen directly. It needs to be transformed first by certain bacteria in the soil into a form that plants can absorb, and then you can absorb from plants. This transformation is called nitrogen fixation. Small bacteria living in the soil and in the roots of certain plants, legumes mostly like beans and clover and peas, take nitrogen from the air and turn it into compounds that living things can use. They have been doing this for billions of years. Without them, all the nitrogen in the world would stay in the atmosphere as a gas, inert and inaccessible. It was these tiny, invisible creatures that made the nitrogen cycle possible. That made complex life possible. But inside you, nitrogen is everywhere. It is in the amino acids that make up every protein in your body. Proteins are the workhorses of biology. They do nearly everything. They carry oxygen and fight infection and digest food and transmit signals between cells and build and repair tissue. Every protein is a chain of amino acids, and every amino acid contains nitrogen. Nitrogen is also in your DNA, in the rungs of that famous spiral ladder that carries your genetic information. The base pairs, adenine, thymine, guanine, cytosine, that make up the code of life, all contain nitrogen. Without nitrogen, none of the instructions for building you could exist. The information that makes you you, that determines your height, the color of your eyes, the shape of your hands, the way your brain is wired, is written in nitrogen. Nitrogen was also forged in the stars. In the same nuclear processes that made carbon and oxygen, nitrogen appeared as a kind of byproduct, a quiet, stable element that would later prove utterly essential for the chemistry of life. When you think about your DNA, that molecule so tiny that a human hair could hold several million strands of it side by side, you are thinking about something that was partly assembled from nitrogen that came from stellar explosions, that drifted through space, that fell with the dust of the early solar system onto the young Earth, that was worked on by bacteria and plants in the slow chemistry of life across billions of years, and that was finally arranged just so in you, in your cells, in the nucleus of every one of your trillions of cells coiled and folded and packed away, your entire biological story written in nitrogen and carbon and phosphorus and the patience of deep time. Your genetic code, the instructions for everything that makes you yourself, is written partly in stardust. There is no way to feel separate from the universe once you know that. Breathe gently. Feel the cool weight of the air coming in, the warm ease of it going out. That nitrogen moving in and out of your lungs has been part of the sky for a very long time. And some of it, once, was the sky of an entirely different world. Have you ever watched the sky just before the sun sets? That hour when the light turns golden and everything seems to slow down. The way the light lands on ordinary things, on leaves, on the surface of water, on the side of a building, and makes them look like they are glowing softly from within, as if the ordinary world has a warmth hidden inside it that only shows itself at certain hours. That light came from our star. Our sun is right now fusing hydrogen into helium in its core, just as those ancient first stars did. It has been doing this for about 4.5 billion years. It is middle-aged, stable, calm. In its daily work, our sun converts about 600 million tons of hydrogen into helium every single second. It has been doing this without pause for longer than the Earth has existed. and it will continue for another 5 billion years or so, until it too exhausts its hydrogen and enters its old age. The light that reaches you from the sun began its journey in the sun's core. But here is a soft, strange fact. That light, in the form of energy, can take a very long time to travel from the core to the surface of the sun. Because the sun is so dense, so packed with matter, the photons, the particles of light, bounce around inside the sun, bumping into particles, being absorbed and re-emitted over and over, making an extremely slow and random walk from the center outward. Scientists estimate that this journey from the core to the surface takes somewhere between 10,000 and 1,000,000 years, depending on the path. After that long, slow interior journey, thousands or hundreds of thousands of years, it takes only about 8 minutes for that light to cross the 93 million miles between the sun and the earth. 8 minutes of space travel after thousands of years inside a star. And when that light lands on a leaf, the leaf uses it to do photosynthesis, to take carbon dioxide from the air and build sugars. When you eat those sugars, or the things that ate those sugars, you are eating sunlight. Old sunlight that has been traveling since before humans existed, that finally arrived at a leaf, was captured, was turned into food, and is now inside you, releasing its energy to keep you warm and alive. You are fed by starlight. You are warmed by starlight. You see the world by starlight. Even at night, the moonlight is just sunlight, reflected off a pale and patient surface. Even the fire of a candle is releasing energy that was captured from sunlight by a plant long ago and stored in carbon bonds. Every fire, every light, every warmth you have ever known has ultimately come from our star. All of the energy flowing through you right now is solar in origin. You are a small, temporary vessel for the light of a star, carrying it for a while, passing it on. The night sky has always made people feel something. There is something about looking up into that enormous darkness sprinkled with quiet points of light that stills the mind. People have always looked up and wondered. Long before there were cities or written languages, people lay on the ground and watched the stars turn overhead and felt something they had no words for. A recognition, perhaps. A sense of belonging to something much larger than themselves. When you look at a star, you are seeing light that left that star long ago. Some of the stars you see with the naked eye are hundreds of light years away. The light you see from a star 400 light years distant left that star 400 years ago, when different people walked the earth in a different world. It has been traveling ever since through the cold of space, and it has only just arrived, and it enters your eye, and you see it as a point of light. You are looking at the past. You are seeing a star as it was, not as it is. Some of the stars you see are already dead. They burned out long ago, but their light is still traveling, and it will not reach you until years or centuries or thousands of years from now. You won't know they're gone until the light stops coming. For now, they still appear as steady, quiet lights. And yet, those dead stars, and countless others we cannot see, gave their atoms to the universe. Those atoms drifted and gathered and became new stars, new planets, new everything. And some of those atoms are in you. You are, in a very real sense, light from dead stars, the matter of exploded suns, reformed and rearranged into a person who can look back up at the sky and wonder. But there is something even more extraordinary. The universe made something that can look at itself. Through your eyes, the universe sees. Through your mind, it thinks. Through your feelings, in a sense, the universe feels. When you feel wonder at the night sky, that is the universe experiencing wonder at its own existence. When you feel the quiet beauty of a star reflected in still water, that beauty is not separate from the universe. It is the universe noticing itself. You are the universe being aware of itself. Just for a little while. Just for the length of a life. Please, if this thought gives you a sense of quiet wonder and peace, consider sharing this video with someone who might need a gentle night like this. A simple like goes a long way in helping more people find this channel. Breathe. Be still. You are ancient and new at once. Let's come back very gently to the body, to the softness of being a physical creature, to the warmth of having a body at all. Your bones are made largely of calcium and phosphorus, arranged in a crystalline structure called hydroxyapatite. It is this structure that gives bones their hardness, their strength, their ability to support everything else. And both calcium and phosphorus were forged in stars. Calcium is made in massive stars through a process called carbon burning. Later in a star's life, when it begins to fuse heavier elements. Phosphorus is made in similar conditions. Both are scattered by supernovae. Both ended up in the dust of the early solar system. Both settled into the Earth. And then, after billions of years of traveling, they ended up in the soil, in the plants, in the water, in the animals, and in you, in the hard, white, strong scaffolding of your skeleton, the structure that holds you up, that lets you walk and sit and lie down in the soft comfort of your bed. Your bones are not static things. They might seem permanent, but they are alive, constantly being rebuilt. There are cells in your bones whose only job is to break down old bone material, and other cells whose only job is to build new bone. The two groups work in careful balance, maintaining the structure, responding to the stresses you put on your body, replacing damaged material with fresh. Over the course of several years, most of the mineral content of your bones is replaced. So, the specific atoms in your bones today were, not so long ago, in the food you ate. Before that, in the soil. Before that, in the rock. Before that, in the sea. Before that, in space. Your very skeleton has come and gone quietly many times during your life without you ever noticing. You are not the same physical substance you were 10 years ago or 5 years ago. The atoms have moved on and been replaced. And yet, you are still you. The pattern continues. The self persists even as the matter changes. There is something tender about that. The body doing all of this work, quietly, without drama, without asking for anything, just building and rebuilding and maintaining itself, using the materials the world provides, not complaining, not pausing, just continuing, for as long as it can, in its faithful way. Your body trusts the universe to keep providing what it needs, and so far, it always has. You can trust that too as you rest. The work is being done. The atoms are in their places. Everything is quietly, patiently, lovingly maintained.